Today I'm going to be talking about uh, Lemma 1 of Theorem 16.16. Theorem 16.16 is just the Lagrange's four-square theorem, which states that all natural numbers can be expressed as a sum of four squares. Okay, so let's move on to Lemma 1. So here's the statement. Let k be an integer, and if p is prime, then there exists integers a, b such that p divides a squared plus b squared minus k, and if n is square free, then there exists integers a and b such that n divides a squared plus b squared minus k. Okay, so let's go over the proof now. So the lemma clearly holds when p is 2 because we can change a and b so accordingly such that they're even or odd depending on the value of k. And now we assume that p is greater than 2 now. And we're going to consider two sets, a and b, which are defined as the following. So a is the set of all a squared, where a is an integer and a ranges from 0 to p minus 1 over 2. So it's 0 squared, 1 squared, all the way to p minus 1 over 2 squared. Okay, and b is the set k minus b squared, where b is an integer and b ranges from 0 to p minus 1 over 2. So it's like k minus 0 squared, k minus 1 squared, all the way to k minus p minus 1 over 2 squared. Okay, so now we'll prove that all the elements of A are different from each other in modulo P, and also that the elements of B are also different from each other in modulo P. Okay, so let's suppose x squared equals y squared modulo P. So like the two elements of A are the same, and then I would say that like they're exactly identical and they cannot be different elements in the set. Okay, so what I claim is that x squared congruent to y squared modulo P is equivalent to x congruent to y modulo P in set A. Well, this is true because P divides x squared minus y squared. We can rewrite x squared congruent to y squared as this, and this implies P divides x plus y, or P divides x minus y. But if P divides x plus y, then x is less than or equal to p minus 1 over 2, and y is also the same. So this implies that P divides x plus y, which is less than or equal to p minus 1. And this can only hold if x and y are identical to 0, as 0. So this also holds. So we kind of proved the injectivity case right here. So we can notice that all the elements of A are different in modulo P, and the same holds for the elements of B. Okay, and now we count the elements of A and the elements of B. We're going to consider like this set right here. So if we notice that the elements of A plus the elements of B is equal to P plus 1, which is greater than P. So if we consider this set, we're gonna have two elements in this set that are congruent to each other modulo P because they're more than P elements. But we know that the elements of A cannot be equal to each other and the elements of B cannot be equal to each other. So we're going to take an element from A and an element from B and set them equal to each other, and that exists clearly because of our past statement. So a squared, there exists integers a, b such that a squared is congruent to k minus b squared in modulo P. Okay, so let's move on to lemma 2. Lemma 1-2 actually. So since n is square free, we can write n as p1 times p2 all the way to pt, where pi are distinct primes. So by lemma 1-1, for each of these primes, there exists integers ai and bi such that pi divides ai squared plus bi squared minus k, right? For all pi where I ranges from 1 to t. And now we use the Chinese remainder theorem, which tells us that there exists an integer A such that A is congruent to A1 modulo P1, A is congruent to A2 modulo P2, all the way to A is congruent to AT modulo PT, and we perform the same thing for B, integer B. Then what happens is that A squared plus B squared minus K will be congruent to AI squared plus BI squared minus K, which is congruent to 0 modulo PI, for all distinct primes pi, where I ranges from 1 to t. And that proves the result, as that means that a squared plus b squared minus k is divisible by n. Okay. Yeah, thank you for tuning in, and see you in the next video.